So today in global ecology and conservation biology, we're going to be talking about population growth. And it's important to realize that a population has a definition, and this is a group of individuals of the same species. That can potentially reproduce. So a species is a group of individuals that can reproduce and produce viable offspring. And so when we're talking about populations, we're talking about all the individuals in a group that are of the same species. And this is different from community, which would be many different species interacting with one another. So generally, population is, if we're looking at hierarchy of complexity, is a little bit more complex than a community is. And we'll actually look at how populations can oscillate and fluctuate. There's a video in your study questions about that. And there's also part of your symbio has to do with the interactions between populations like the wolves and the moose. Okay, so when we look at growth, you'll see in your book that there is kind of a weird way to denote growth. And this is actually calculus. So you don't really need to know the formulas or how to calculate growth. But this is just a change in population size over time. So this is N would be the number of individuals in the population, and T is over time. So this is the change in the number of individuals over time. And in its simplest form, this is essentially just the birth rate, the number of births minus the number of deaths. So we can say that this is equal the number of births minus the number of deaths. Now, the first example that we're going to talk about of a population growth model is that which is represented by exponential growth. So one thing that does grow exponentially would be bacteria, and they actually can reproduce by simply dividing themselves into two. So one individual can double and produce two individuals, so they don't have to reproduce sexually. They can just double by dividing themselves. And so exponential growth has a particular shape, and this is a J-shaped curve. And this is different from other types of growth where we have an S-shaped curve. And so when we talk about the J-shaped curve, there's generally not a little line over it. But if we look at a graph here, this is time, and this is the number of individuals. So what happens is that it starts out relatively small, and then you have this dramatic increase over time. And so it becomes a J-shaped curve. So individuals is increasing along this axis, and we have an increase in time along this axis. So if we look at exponential growth, we can talk about a value which is called R max. And so R max is the maximum rate of intrinsic growth. And so, for example, if R max equals 2, that means that one individual will produce two offsprings. So this means one individual can produce 2 offspring. Now, when we talk about Rmax, most species do not reproduce at their maximum rate. And so it would be like, if you were thinking about humans, it would be like, how many maximum possibility could a female, for example, how many total offspring could she produce in her life during the time period where she's fertile? And so generally we do not. We are not have a maximum rate, but some species do. And we actually looked at another term, which was referred to as R-selected species. So R-selected species are versus K-selected. So R-selected species are known to have a large, high reproductive rate and to produce lots of offspring. And they don't generally provide a lot of extra care for those offspring, and the offspring tend to die. So if you think about mosquitoes or other insect populations, they are selected, and that refers to this idea of Rmax, that they tend to maximize their rate of intrinsic growth. Now, when we look at the formula for exponential growth, there is a formula. So this would be the formula for exponential growth. And we're going to talk about logistic growth in a minute. But N over T, and so this is the number of individuals in a given period of time. So this is the population size, is equal to N sub 0 E R max times T. So when we look at this formula, and you'll be using some of these formulas in your Symbio, N sub 0 is just the population at the very beginning. Now E is actually a constant. So it is a mathematical constant like pi, and it is approximately 2.72. And so if you have a fancy calculator, you might notice that you have the ability to calculate e to the x, right? And so this is actually just 2.72 to a value, an exponential value. And so, for example, you could take the Rmax and the number of years, and that is a function of this e times n sub 0. So, for example, if we started out where we had, we go use to a different page. Where n sub t is equal to 4. So that's the initial population size. And then we have 2.72, that's E. And then we have the R max, which is 2. And then we have, in this particular instance, 2 years. So this is actually to the 4th. So N over T, and I wouldn't make you do this on the test or anything, but if you calculate this out, so this is to the 4th power, if you calculated that out, that would give you 30. So that would be the population size of 2 years if you just start out with 4 individuals that are able to reproduce. Now, the crazy thing about this is that this seems like a really small number, but if you increase the time, remember our exponential growth pattern is that the population will grow really, really quickly over time. So let's just do a different example of this where we have n sub t equals, we'll start out with 4, so that's our n sub 0. And then this is E, 2.72, and we'll use the same R max, which is 2. So one individual can produce 2 individuals in a given period of time. And instead of 2 years, we're going to use 10 years. And so if we look at what this gives us, this is 1.9 billion, right? So that's a huge number. So in only 10 years, we get a large population size. So the thing about exponential growth is we don't generally tend to see it very often in nature. And the reason for that is that there are limiting factors to growth. Things generally do not maximize their reproduction because of the resources in the environment. So the resources in the environment are going to limit oftentimes the growth of the population. Okay. So we can talk about limiting factors, and we can talk about two different types of limiting factors, those that are density independent. So density is just the number of individuals in a given area. Okay. So this means that it is not dependent upon the number of individuals in a given area. So this is due factors that are not due to or are not related to the size of the populations. Okay. So this is often associated, these factors are often associated with weather. So for example, if storms regularly come in and wipe out a certain given number of individuals in the population, then that is going to limit the growth rate. Also drought. So if we're talking about amphibians in the desert, obviously rainfall in a given year over a given period of time will limit their ability to reproduce. So probably more important than density independent is the density dependent. And so these are related to population size. So for example, the amount of food, the amount of space, also disease, because as organisms are crowded in with one another, there is a greater likelihood that disease will spread from one individual to another. So we could put disease, we could put food, we could put space. So if we're talking about nesting sites, right? We could also talk about in terms of density dependent. We could talk about waste removal. So sometimes when organisms become too dense, then we start to see a buildup of waste and a degradation of the environment. And so that could be like urea, or urine, or feces, right? You have to get rid of that waste. And that might, because waste might take up space, and it might also lead to disease, and it might make individuals die, right? So that would be density dependent factors. So these tend to slow population growth through a negative feedback mechanism. Oops, tend to slow population growth through negative feedback. And remember that these negative and positive feedback doesn't have to do with whether they are good or bad. Like, it's not a positive in that it's a good thing. Positive feedbacks actually tend to lead to unregulated growth. So negative feedback is actually a pretty good thing in terms of maintaining homeostasis in a system. So what happens is as the population increases, then you get an increase in the density dependent factors. So the population increases, the density dependent factors kick in, and so they're going to slow population growth or reduce the population growth. And so this helps to maintain a relatively constant population size. So if we look at this type of reproduction, this is what is referred to as logistic growth. And it has a different equation than the exponential growth equation that I showed you. And so the change in population size over time is equal to R max. So there's no E in this particular one. And this is N. So this is the population size. And then we have K minus N over K. Okay. And so K is equal to carrying capacity. And carrying capacity, we'll talk about in a lot more detail, but carrying capacity is the maximum number of individuals that the environment will support, okay? So this is the maximum number of individuals that an area will support. So the resources that are needed to support. Okay, so as this N starts to approach K, then you'll notice that this will go to 0. So like if we put K and N in 1, so for example, if we put like 1 minus 1 over 1, right, that would be 0. And so then that is going to slow population. So this is actually an S-shaped curve. And we also talk about K-selected species. And so humans are a K-selected species rather than an R-selected species. And so this is where that K comes from, is this logistic growth and the carrying capacity. And when we look at the K-selected, this means that they do not grow at their R max, that this carrying capacity up here limits their growth and slows down the growth. And so when we look at K-selected species, remember that they produce few offspring that generally need lots of care. So they have a different reproductive strategy than the R-selected. So elephants would be an example of a K-selected species. So if we look at our graph, this is one of the graphs that you need to be able to sketch on the final exam. So this is number of individuals or population size. Okay, so population size would increase. And so instead of seeing that J-shaped, what happens is we start to see this S-shape, and it comes up here, and then it starts to level off. So this is the S-shaped curve. And oftentimes with logistic curves, you also see a dotted line. And so this dotted line comes across, and this is the carrying capacity. So K is equal to that dotted line. So as the population first starts to grow, it grows at a high rate. And then when it starts to reach the carrying capacity, it starts to slow its growth. Now, oftentimes what you'll see is kind of an oscillation around K. And that is because sometimes the populations overshoot the carrying capacity. And then there's a time lag where it takes a little while for the individuals in the population to feel the effects of the density dependent factors on their population growth before that goes back and decline. Okay, so you get that oscillation oftentimes in a logistic growth. Okay, so this shows that S shape, right? And this is kind of interesting because this is time and population size, but then what they did is they showed how the population size affects population growth. So you'll notice that population growth is greatest at an intermediate size. So population is slow, growing is slow here and here, right? But when the population is of a medium size, then the population is growing faster. It's a little different way to show it. So when I'm asking for logistic, I'm not asking for this graph, but I'm actually asking for the S-shaped graph. Okay, so when we look at the carrying capacity, we need to talk about resources. And the resources that our population needs are sometimes referred to as environmental goods and services, okay? So this is the max number of individuals. Oops, my pen's not working very well. Of individuals that can be maintained in a population, So this is from your book, a definition from your book. That can be maintained sustainably, and so indefinitely. Okay. Oops. Oh dear. Let's start down here. I might need to select that message and restart options. We'll just do off. We don't want the computer turning off on me. Okay, so the number of individuals in a population that can be sustained indefinitely by the resources in that given area. And again, it's the letter that is used to designate carrying capacity would be K. So if we look at an example of this, scientists try to go in and they try to figure out what kinds of resources are important in determining the carrying capacity of the environment. So if we look at frog, for example, so this is just a hypothetical example looking at the environmental goods. So that would be like hiding places. So the requirements for frogs are 2 meters squared. So each frog needs 2 meters square. And if the pond is of this size, then it is 120 frogs can live in there. And then the water processing. So this would be like when the frogs urinate into the water and they defecate into the water. And so this would be waste processing. And it can only process the waste of 100 frogs. We can look at egg laying spots. There's 120 mated pair space for those mated pairs. And if you look at food, if you just looked at food alone, then there could be a lot more frogs. So this is actually the carrying capacity right here. So instead of 120 frogs or 500 frogs, there's only the carrying capacity of 100 frogs, just simply because waste processing is the limiting factor. And that is a density dependent limiting factor. Okay. And as I mentioned before, populations can fluctuate. So if we look at population size over time, we can see that it can come up to the carrying capacity, go over the carrying capacity, and you can see something like this. So this is my carrying capacity. And one of the really interesting things, I didn't really draw that in the right spot. One of the really interesting things, if I look at my carrying capacity, is that however much you go over the carrying capacity, so you've got that too many individuals, then you go down below it. And so if you exceed the carrying capacity by a lot, then you tend to have a dramatic oscillation. Okay, so these are oscillating population sizes. And again, time lags can be important. So the longer the time lag between the effect that the overpopulation has on reproduction, the greater the overshoot there will be. Okay, so all of this leads to a discussion of human populations. And when we look at the human population, it was relatively stable for a long period of time. And then something happened, and that something happened was primarily agriculture. So if we look at human population sizes, for the human population, our current population, which you can actually get by typing in your Google population clock. So the population clock counts the number of individuals on the planet or in different countries. And so today, the population clock worldwide is 7.4 billion individuals about. So this is billion. So we've exceeded 7 billion, and we're on our way to 7.5 billion. Okay, so this is on the planet. In the US, it's kind of interesting. There are, in the US, 325 million people currently in the US. And obviously the US population, if you see the clock, it's actually ticking a little bit slower than the planet, because in some parts of the world, reproductive rates are higher than they are in other parts of the world. So if we look at our population, we can see that it was under 1 billion for a great deal of time, recorded history. Prehistory, we're not sure, probably was smaller, but this is 1 billion, right? So it took us a while to get to 1 billion. And you can even see here, this was the plague. So that was a major disease that wiped out like 1/3 of all Europeans. So that gives us a big dip. And then if we look at here, this is the Industrial Revolution. And so we see that after the Industrial Revolution, we have a dramatic increase. So this is actually a J-shaped exponential curve. So the question that is posed to you by the textbook is, are humans affected by the human population size? Is it constrained by a carrying capacity of the planet? So we'll talk a little bit more about that. So when we talk about growth rates and this increase in growth rate, so increase in population size was due to, one, this would have been the decrease in the death rate. So individuals produce a certain number of offspring, and in the past, it was not always assumed that those offspring would survive to reproduce. And oftentimes, children died. We had infant mortality, death at birth. Children typically did not make it past the age of 5. And so just simply by decreasing the death rate through medicine and sanitation, for example, we saw an increase in the human population size. So this is a good thing, I think. Sanitation and medicine. We also see that we also have a decrease in starvation, right? Actually, food supply. Okay, so the other thing would have been agriculture. So instead of being hunters and gatherers and dependent upon the native trees and plants and animals for our food, we actually started settling down and developing types of food and selecting types of food that would support larger populations. So agriculture, which was about 10,000 years ago, was kind of a big deal in terms of human population rates. So we can also talk about fertility rates. And the fertility rate is, in general, the average number of children women will produce in their lifetime. So being an average, it is not generally a whole number. So if we think about replacement rate, if you have, because we reproduce sexually, you have a man and a woman. So in order for them to replace themselves in the population, their fertility rate would have to be 2. So 2 is the replacement rate, assuming that there is no death. No death of children. So if we look at the fertility rate of the US, the replacement rate is 2.1. So in the US, the replacement rate is 2.1. And that's because some children will not survive to reproduce themselves or might not survive to adulthood. And then in other places where there's a lot more children dying, the replacement rate in Uganda, for example, is 2.5. So they have to have 2.5, on average, 2.5 children. Each female would have to have 2.5 children in order to keep the population growing at a steady pace. So when we increase fertility rates, that is also going to increase population growth. And so if we talk about an increase in fertility rates, what causes this? Okay. This generally is in places where women marry young and start having babies at a young age. So as soon as they're able to produce children, they start producing children. So women marry young. And have children young. And then the other thing is they have a high infant mortality. So if your children are, your children are going to die, you tend to produce more of them. Okay. So we can also look at in the worldwide what decreases fertility rates. And this has to do with education. So a safe, reliable birth control education, but also just education in general and employment opportunities. So birth control availability allows for family planning, right? And then education and employment opportunities for both males and females. So when we look at the worldwide fertility rate, it is decreasing. So in the 1950s, and this is worldwide, so this is not in the US, in the 1950s, the fertility rate was 5. So every female was producing on average 5 offspring, right? In the current fertility rate worldwide is 2.4. So we're decreasing the number of offspring that we're having, but the population size is still increasing because exponentially it depends upon population. So that initial population size will tend to continue to cause an increase in the population as a whole. Okay, so we just talked about fertility rates. Okay. So this is interesting. So this shows worldwide the fertility rates are decreasing. So this is 1975 is blue and 2012 is red. Okay, so we see an increase or decrease. Interestingly, in the US, from 1975, we actually see a slight increase in fertility rates. Now we can also look at population histograms, and what these are graphical representations of the number of individuals that are in each age group. Okay, so this is the number of individuals sorted into age groups. So let's just look at a hypothetical one that your textbook provides. And Fredonia is the hypothetical. And so you'll notice that the number of individuals in the 0 to 9 is greater than at the 70 plus. So this would be a population that is going to actually increase in size because we have a large base and it's kind of a pyramid shape here. So this is just categorizing people and putting them into different age groups. So if we look at the different countries, when we see a pyramid, so a pyramid-shaped histogram, this is a population growing. So the example is 2005, but that is Mexico. And so you see that there's the big base. These are the young people, and they're going to come up and they're going to have babies. And even if the fertility rate stays the same, then the population is going to increase over time. Then we have the rectangular shape. Right? And that is the population is staying the same. So Denmark, for example, is approximately a rectangle, right? And so the population is neither decreasing or increasing in general. And then if we have an inverted pyramid where the base is smaller than the middle, this is the population is shrinking. And you probably heard stories about this happening in Italy and other European countries where the fertility rate is not replacing the population. And so there is some concern that if these individuals, when they get up there and into their older years, there's not going to be enough people in the population to support them economically and maybe even physically, like taking care of them. And so population, we have to kind of figure out how we're going to deal when populations decline. How do we deal with that period of time where your population is aging and most of the people are over the age of 60, for example? The US has a really interesting example here of the baby boomers. So after World War II, beginning in 1946 and extending into the 60s, we have the baby boom generation. And so after World War II, people started having babies. And so you can see how this cohort has moved up the pyramid as they age. And so what they did essentially is that they widened the base. So this base was smaller and now it is wider, right? It's rectangular in shape here. And that's because it's approximately staying the same. But there is some concern that when baby boomers start collecting Social Security, which they have started, that we're not going to be able to support them economically with the wages that are being earned by younger people. Okay, so Thomas Malthus was a philosopher and an economist in the 1700s. And he proposed a dilemma. He actually wrote an essay warning in the 1700s of a dramatic population crash. And this was echoed by Paul Ehrlich in the 1970s with the population bomb. And this was the warning that if we did not curb our population growth, that we were going to overshoot the carrying capacity and we were going to crash. And so in the Malthusian Dilemma, this is the idea that the food increases in a linear fashion, but the population is increasing exponentially. So the population is increasing, and he saw this in Europe, in England, is increasing exponentially, while food production is decreasing, not decreasing, increasing linearly. So it is not going to keep up. So what his idea was is that humans were going to overshoot the carrying capacity. So in this diagram, you see linear means a straight line. right? Exponential is that J-shaped curve. So as soon as it overshoots the food, then you're going to have a shortage of food and the population is going to collapse. The interesting thing is that this did not happen. And some people argue that the carrying capacity cannot be applied directly to humans because of a couple of things. One, we are always increasing our technology. And so as we increase our technology and we become, we use our minds to increase our resources and the goods and the services, then we can increase our number of individuals that we can support. And the other thing is that humans are not limited to the resources that are right by them. So for example, in Oregon, we're not limited to only the resources in Oregon. We're not even limited to only the resources in North America, right? So if we need oil, for example, or other resources, we can import them. And so we're kind of, we can always go someplace new and colonize it and then take those resources or trade for those resources, right? And bring those resources to us. And it's interesting that we are still growing. So the question is have we overshot the carrying capacity yet? And does carrying capacity even apply to humans? So one of the interesting things about human population growth is that we see what is referred to as a demographic transition. So the study of population structures, like those age structures, those histograms we talked about, is the study of demography. And demography changes depending upon the level of development, quote unquote development, in a population. And it tends to go from a population that has high death and high birth rates to one with low death and low birth, okay? So this is population change over time. So the transition from high death and birth rates to low death and birth rates. So populations generally grow really slowly if there's both high death and birth rates. But once you start decreasing the amounts of death through like clean water and sanitation, then the population starts to grow. But as soon as the populations become economically stable and people have access to resources that are more than just survival, for survival. So we have, instead of just food and shelter and clothing, we have iPods and computers and cars and all those other things that kind of make life, you know, our affluence. Then the death and the birth rates both decrease. And so this is shown through these stages. So notice here that the population is not growing, right? Population grows when we decline the death rates. And then once we get into modern stability, then they will it'll become stable. So this is the death rate right here. So here's crude birth or death rate. Okay, so this is the death rate decreasing and the birth rate. So notice that the death rate increases first, which is followed by a decrease in the birth rate. And so in Mexico, we can see that it is actually in phase 3, right? So birth rates are starting to decline in Mexico. And that could be because of birth control. It could be because of family planning. It could be because you have less babies dying. It could also be because women are interested in getting an education and also working. And so they're not having babies really early on. And so education and employment by women are going to decrease the birth rate. And so in Sweden, we see that there's very low, right, rate, so of birth and death, right? They kind of, it's stabled off so that the population is not going to increase or decrease over time. It's going to stabilize. Okay, so humans, as I mentioned before, have expanded our use of the environment. So we're not dependent upon resources in our resources, goods, and services in our immediate area. Okay, so not dependent upon resources, goods, and services in our immediate environment. So a good example of this that your textbook uses is New York City. And you might have heard the problem with the garbage disposal in New York City is that there's no place to put it in New York City, right? So I don't know how many years ago it was, but they had big barges of garbage. They were going up and down the coast and nobody wanted New York City's garbage. And so they were just kind of stuck in this state of limbo, right? And so New York City can be densely populated because it can get its resources from other places and then it can ship its waste out. So this is a kind of explanation for why carrying capacity does not apply necessarily to humans. Another good example is Japan, where you have a very large population living in like a resource depleted environment. So they don't have a lot of their own resources, but they produce goods and services so that they can trade for the resources that they need to sustain their large population size. So this is an example. So in your book, they have an interesting map that shows our uses of crude oil. Oops. So our uses of crude oil. So this is crude oil imports. And so you can see here that like if you looked at South America versus North America, we are dependent upon bringing in fuel, right, in order to support our lifestyle much more than other places in South America, for example. Okay, so, and then, I don't even know where Africa is located. We kind of need to, they look so much different. I think this must be Australia, right? India, okay. So this just shows us that we are hugely dependent. Our lifestyle is not powered by our resources in our immediate environment. We are utilizing resources from all over the planet to survive and to have this large population, but also this affluent lifestyle that we live. Okay, so in terms of the human carrying capacity, we have two groups of people, and these are referred to as the resource pessimists versus the optimists. So the resource pessimists say that we have overrun the carrying capacity. So humans have exceeded the carrying capacity and they are going to decline. And that we are bound by the same rules, natural rules that govern other populations of animals. Okay, so that would be a pessimist. An optimist would say that humans have not exceeded the carrying capacity, right? Humans can increase the carrying capacity through the use of technology. Okay, so those are the optimists. And so in your book, they have some charts. One of them has to do with, this is an interesting example. It's a pessimist. This is the example of fishing industry. And so when we look at the amount of fish that are caught, millions of tons, we see that it has leveled off. So we had this dramatic increase between 1950 and 1990, and now it's starting to level off. And you could actually is starting to decrease because we've overfished and overharvested the oceans. So in order to compensate for this, we are creating fish farms, right? So through technology, we are supplementing the amount of protein that we got through wild catch with farm fish, right? So that would be an example of kind of a resource optimist perspective. The pessimists say that with a shortage of resources, environmental degradation, right, this is going to cause the collapse of our natural ecosystems and loss of environmental services. And really, climate change is really going to test this to see if this is true, because it might dramatically affect oceans, but it also might dramatically affect our water supply and also drought, so natural precipitation, patterns of precipitation. So the optimists say that we can, oh, hello, I'm almost finished. Okay. So the optimists say that we can increase our carrying capacity through the use of technology in these various ways. Okay, so that will be the end of this particular lecture, and there will be more for this unit later on.